All right, so here's problem number 15 from section 7.3 from our calculus book. We're going to find the volume of the solid generated by revolving a particular region around the x-axis. Let me start by drawing the region in question. Okay, it is bounded by the line y equals x and the line y equals 1 and the line x equals 0. So let me actually highlight that all in blue. So that is indeed a triangle. And this is going to be then revolved around the x-axis. So the way we start trying to visualize this in 3 dimensions, I start by drawing the reflected image across the axis of rotation. I choose corresponding points and I'll make ellipses. And maybe in the interior here, I got a center of rotation. I've got a point on this curve, corresponding point on its reflected curve. Maybe up here for an arbitrary x, I've got another point. Now, if you're trying to visualize this, I think I would visualize this as a cylinder. And inside the cylinder, a cone has been drilled out of the center of it. Okay, flat sides and then diagonal interior. Right? Now, let's talk about trying to find the volume of this. Okay, so we know that the volume is going to be the integral from A to B of a cross-sectional area times a bit of thickness. And in this case, that thickness is considered dx. That thickness would be measured horizontally. If I try to pinch it between my fingers, I'd be measuring that distance horizontally. And anytime we measure things horizontally, it's measuring in the x direction. Now, I say we draw the picture big, did that. I say we label some coordinates. I'm going to start here at the center of rotation. I'm going to call that x comma 0. I'm going to go here, which is on the edge of the smaller of the two circles. I would call that x comma x. And then I'm going to go here on the far outside of the big circle, and I'm going to call that x comma 1. I think the cross-sectional area, because it's an annulus, because it's a circle with a circle in the middle removed, I think the cross-sectional area in general is pi big R squared minus little r squared. I think in this case, the big R squared is the distance from the center of rotation out to the far edge. I think the big R squared is x. Sorry. Big R squared is 1. And I'm going to square that. I'm going to say the little r squared is from here to here. And I think that that distance is the difference between 0 and that x, the difference in the y coordinates. I'll call that distance x, and I'll square that. And the last thing I need is my limits of integration. I had asked the question, what is the lowest x for our original region? That looks like a 0. The highest x for the original region, and this is the intersection of y equals 1 and x is equal to y. I think it's pretty clear that that far right-hand side of the region is 1. So I think the integral from 0 to 1 of pi times quantity 1 squared minus x squared dx is our expression. Let's finish this off. My habit is to pull the constant pi out. Let's clean this up as 1 minus x squared. Pi times x minus 1/3 x cubed. Double check me, please. And we're going to evaluate that from 0 to 1. How about pi times 1 minus 1/3 times 1 cubed, 1/3 times 1 cubed. That's our evaluation at the high end. At the low end, I get 0 minus 0, which I can effectively ignore. I'm looking at pi times 2/3 is my answer. And they agree. Yeah. Yeah, I mean, you could put a bracket there. I know that we have a tendency to always write that as a bracket. I don't think there's any rule that that has to be a bracket or a parenthesis. All right. Any other question? All right.